Hi there, folks. Today we're looking at solving linear equations. There are two key elements to this, and these key elements are kind of the foundation for solving all equations, though some of that might look a little different depending on the type of equation we have. But the idea here is to work backwards sort of operations and use inverse operations as we go. And first of all, the reason we have to work backwards sort of operations, order of operations is kind of like the rule book for how to simplify expressions. It tells us the procedure that we have to follow. And if we want to undo that, that's what solving an equation is. We have to go backwards through the process when we undo something. It's this idea of reverse engineering. For example, imagine for a moment that I took a piece of paper and I wrote you a message on it, and I folded up that piece of paper and I placed it on the table, and then I put a book on top of that piece of paper and then covered that book with something like a box. All right? If I now ask you, so think about the process I just went through, the order I did those things, wrote the message, folded it up, covered it with a book, covered it with a box, okay? But now if I asked you to read that message, your only option is to undo the process that I just did. So you have to remove the box. Then you have to remove the book. Then you have to pick it up, unfold the piece of paper, and then read the message. And notice the steps that I just described are reversed from what I did. See, what I did was I folded it up, put a book on it, put a box on it, all right? And then to undo that, you have to remove the box, remove the book. So we're working backwards. To undo a process, we have to go backwards through the process and undo the pieces that we did. That's the idea. So we're working backwards through order of operations, and we're using inverse operations. We're working backwards through the process, and we're undoing the things that we did. All right. Inverse operations. Remember, order of operations, I like to do IRMDAS, and I always write it this way. You can use PEMDAS. That's fine. All right. We'll use that E and that R later in the course. But the idea here is, addition and subtraction were tied in order of operations, but also they're inverse operations. If I want to undo addition, I use subtraction. If I want to undo subtraction, I use addition. Multiplication and division, they're inverse operations. They undo one another. And then we'll use later in the course, exponents and roots are inverse operations. They undo one another. And so that idea that every operation can be undone with a different operation, all right? But now we have to work backwards through this process as we go. See, when we simplify, we do inclusion symbols, then exponents and roots, then multiplication, division, then addition, subtraction. But if we want to work backwards, we want to undo that process. We have to undo addition, subtraction, then undo multiplication, division, then undo exponents and roots, okay? And then undo inclusion symbols. So we're working backwards using inverse operations as we go. For example, if I look at this guy, think about what's happening to x. See, if I knew what x was, I would multiply it by 2 and then add the 1. That's what order of operations says, all right? But to undo that process, I have to undo the last thing that I did. So instead of adding 1, I have to undo that, and I do that by subtracting 1. And remember, with solving equations, whatever we do to one side, we have to do to the other side. All right, it's all about balance here, okay? So I'm undoing the process. That gives me a 2x equals a 6. And now to undo multiplying by 2, I have to divide by 2. And that's it. Okay, now I know what x equals, and I could easily plug that back in and follow the order of operations to check it. All right? If I look at this one, again, I want to work backwards through order of operations. So right now, it's x divided by 4 and then adding a 3. That's our order of operations. But I have to undo that process, so I have to undo adding the 3 first. And I undo that by subtracting 3 from each side. Make sure you do it to each side. That's a negative 5. And now to undo dividing by 4, I'm going to multiply by 4. And again, whatever I do on one side, I have to do to the other side. So I get negative 20. And once again, I could check that by plugging it back in and following order of operations. But to undo the process, all right, I have to work backwards through order of operations. If I look at something like this guy, once again, it's times 1/2 and then minus the 4. So I undo addition and subtraction first. I'm working backwards through order of operations. To undo subtracting 4, I'm going to add 4. Whatever I do to one side, I have to do to the other side. And so now what I have is a 1/2 equals 9. And then from here, you might go, oh, well, to undo multiplying, I divide. So I divide each side by 1/2. Ugh, gross. All right. I do not like dividing by fractions. Nobody likes dividing by fractions. You tend to make mistakes when you do things like that. Think about what a fraction bar really is. A fraction bar is a division sign. By saying 1/2, I'm saying divided by 2. All right. That fraction symbol is the same as a division symbol. And how do I undo dividing by 2? Well, I multiply by 2. Okay. And so always think of it kind of like division and think about undoing it using multiplication. It's better that way. You'll make less mistakes. So here, 2 times 1/2 is a 1. So I'm left with x. Over here, that's an 18. And again, whatever I do to one side, I have to do to the other side. That's that idea of bringing balance to this thing. If I look at this one, once again, think about the fraction in a different way. It says times 3/4. But really, that's a division sign, right? A fraction bar is a division sign. So it's saying times 3 divided by 4. And I know how to undo that stuff. I can undo dividing by 4 by multiplying each side by 4. See, now the times 4 and the divided by 4 cancel out, so I'm just left with 3x. And now how do I undo multiplying by 3? I divide by 3. Again, whatever I do to one side, I have to do to the other side. And there it is. And here's the thing. When you think about a fraction is just multiplication and division happening at the same time. 3/4 is times 3 divided by 4 at the same time. So if you wanted to, we could take this a step further. If 3/4 means I'm doing those two operations at the same time, I could undo them at the same time, right? So I could undo them by multiplying by 4 on each side, just like I did in the previous version of this thing. But at the same time, couldn't I divide by the 3? Watch this. Divided by 3, divided by 3. See, I could use a fraction. It's actually the reciprocal to undo both operations at the same time. Undo the multiplication and the division at the same time. And so what happens is I'm left with x. And over here, 6 times 3/4, it's like times 4 divided by 3, or divided by 3 times 4, still gives me an 8, okay? So either think about it as two operations, think about that fraction bar like a division sign, and it makes looking at some of these things a lot easier, okay? But you can undo them simultaneously. If I look at something like this guy, many of you are probably going to go, oh, go ahead and distribute. I don't want to do that yet. Let's pretend that I don't know about distributing yet. We'll do that a little bit later. You can approach this the same way, working backwards through of operations. And so think about what I have. I have addition, but it's in parentheses. That's inclusion symbols. And I have multiplication. So the question becomes, do I undo the multiplication first, or do I undo the parentheses first? And again, if I'm working backwards through of operations, I undo multiplication first by dividing each side by 3. See, now I can undo what's in the parentheses. So I undo multiplication. Now I'm going to undo what's in the parentheses. To undo what was in the parentheses, I'm going to subtract the 2 from each side. And I get x equals 2. Now, if you had distributed and followed that kind of progression through this thing, you'll get the same answer. And that's okay. But I want you to understand that idea of parentheses and saving it for last. I can undo the stuff outside parentheses and then undo what's in the parentheses. That's still me working backwards sort of operations. And I like to show that one before I show this next example, because this next example has invisible parentheses hiding in it, okay? Anytime I have an operation happening to an entire group of things, that group of things is in parentheses. And invisible parentheses will really mess with us sometimes. But see, in this example, you see the subtraction, you see the division. Subtracting 6 divided by 7. Students will often say, well, why do I multiply by 7 first? Because that's what you have to do here. You're probably thinking, well, shouldn't I undo the subtraction first? So I should add 6. That's not the case, because, see, that division sign, this entire thing, the entire x minus 6 is being divided by 7. So there are parentheses around that x minus 6. Even though they're not written, there's invisible parentheses there. So just be aware of that, all right? There's automatically parentheses implied around that thing because that division sign applies to the whole thing. See, now it's just like the example I just did. I have to decide, do I undo division first or undo the parentheses? And the answer is I undo division first. So to undo dividing by 7, I'm going to multiply each side by 7. Now I'm left with what was in the parentheses. And to undo what was in the parentheses, I'm going to add the 6 to each side. Okay? So be aware of that. Anytime we have an operation happening to an entire group of things, that group is automatically in parentheses, which means I save it for last in terms of solving because I'm working backwards through order of operations. If I look at this guy, once again, same kind of thing, that 2x plus 3, that entire thing is divided by 5, which means there's invisible parentheses here. It's implied that that thing is in a group, all right? So there's parentheses around that. So now I undo the division first. So I multiply by 5. That's how I undo the division. So it leaves me with what's in the parentheses equals 15. Now I can undo what was in the parentheses. And once again, I'm still working backwards through order of operations. So inside the parentheses, I undo the addition first. So I subtract the 3 from each side. And now I undo that multiplication. Okay? So the foundation for solving equations is working backwards through order of operations, undoing those operations as we go, all right? And making sure we do the same thing to each side of the equation, all right? And there's some little things we have to worry about, like invisible parentheses, okay? Let's look at some of the more complicated examples. Ready? Simplify and then solve. This is what many of you wanted to do when we saw that distributive property that we could have done. You are allowed to do the distributive property. In fact, sometimes you have to do the distributive property first, okay? So simplify by doing things like the distributive property, simplify by combining like terms, that kind of stuff, and then solve the same way we've been solving. For example, if we look at something like this guy. Right away, I should notice that I have the ability to use the distributive property here, so I'm going to distribute that 4. So I'm simplifying and then solving. So I distribute, that's an 8x plus 20. And now I can continue to simplify. Anything that's on the same side of the equation, I can apply order of operations to. See, that's what I'm doing. By simplifying, I'm basically saying, okay, let's work through order of operations. Let's combine like terms. Let's add, subtract, let's multiply, let's do operations. All right? Until I get to a point where I can't, once I'm ready to solve, then I'll work backwards. So I'm working forwards right now, which seems strange. But these are on the same side, so I can combine them. If they're not on the same side, then I'm not allowed to combine them. Now, I've gotten to the point where I can't simplify any further, so now I hit the brakes and say, okay, now let's solve. Now let's undo the operation. So I undo the addition by subtracting the 20 from each side. And then I divide by the 4. So I end up with x equals 3. Done and done. Okay? But that's the idea here. We're using operations, order of operations, to simplify. And then once we can't simplify any further, we hit the brakes and we go into solving mode where we're working backwards. Okay? And in that particular example, I had to distribute first because I can't just divide by the 4. I mean, I could, but it would be very confusing as to which pieces end up getting divided. Okay? So simplify and then solve. So here, I'm going to simplify by using the distributive property. But now I can also use my distributive property here. I'm going to distribute this guy. And keep in mind that that minus sign goes with the 4. It's like a negative 4 being distributed. So here, this is a 3x plus 15. That's a minus 4x minus 4. Again, distribute that negative with it. Okay? And now I can combine like terms. The x's combine into a negative x. These guys combine into an 11. And now I can't simplify any further, so I hit the brakes. Now we go into solving. Undoing operations. So I'm going to subtract that 11 from each side. And then divide by the negative 1. And some teachers will tell you to multiply by a negative 1 there. That's fine. Same thing either way. Okay? I'm just trying to change the sign. See, and again, when you look at a minus sign or negative, it's really an opposite sign, really, when you think about it. You know, numbers are negative, but variables you just want the opposite of that. So the opposite of x is a negative 14, so x is a positive 14. Okay? It's kind of how we read that. Let's talk about variables on both sides. If I have variables on both sides, I still want to do the same kind of stuff, simplify and then solve. But at some point, I need to get the variables on the same side. I can't have variables split on different sides. And, a lot of times teachers say what I just say. We want to get variables on the same side, but really it's more about we want to get rid of variables from one side, okay? I can't have them split up, so one of those sides, I need to get rid of the variables, all right? And it's more that way than it is moving them to the same side. For example, if I look at this guy, right now I have variables on each side. I've got a negative 8x on one side, I've got a 4x on another side. I can't combine them because they're not on the same side. I only want variables on one side, which means I have to get rid of variables from one of these, okay? And I always get rid of the thing that's smaller, all right? When you think about the idea of moving it, quote unquote, we always want to move something that's smaller because that's easier. So between a negative 8x and a positive 4x, negative 8 is smaller, so I'm going to get rid of the negative 8x. So think about, how do I get rid of a minus 8x? I use the inverse operation. I add 8x. And whatever I do to one side, I have to do the other side. So it's that same concept of undoing operations and making sure I do the same thing to each side. And really, I could have subtracted the 4x from each side if I'd wanted as well, all right? But now I can continue to solve, and I always deal with variables first. Not that you have to. You could subtract the 7 from each side. You could add the 17 to each side. I could add an elephant to each side, okay? I could add a million to each side. It doesn't help me, all right? But I'm allowed to do whatever I want to each side of the equation. The best thing to do, and the thing that helps me the most, is dealing with variables first, okay? So always deal with the variables first. Now, because I'm solving for x, it's 12 times x minus 17. I want to solve for x, so I want to undo the operations that are over here with x. So I want to undo subtracting the 17 by adding 17. Let's see, that's a 24. And now I undo multiplying by 12 by dividing by 12. So I get x equals a 2. Done and done. Okay? If I look at the next one, once again, I can use my distributive property. So I'm going to distribute. I want to simplify and then solve. So I simplify by using my distributive property. 1/4, remember, 1/4 is like divided by 4. So 1/4 times 16 is just 16 divided by 4. Same thing here. 1/4 times 60 is just 60 divided by 4. And now I can't really simplify any further in the traditional sense. I have to start solving, and that begins by making sure I only have variables on one side. So I look at the 9x and I look at the 4x. Which one is easier to get rid of? Which one's smaller? I'm going to get rid of the 4x. And because it's a positive 4x, I get rid of it by subtracting 4x. Whatever I do one side, I have to do the other side. Okay, it's about eliminating one of those x values. And now I can solve in the more traditional sense, working backwards sort of operations, undoing the operations as I go, undo the subtraction by adding to each side, and now undo that multiplication by dividing each side by 5. Okay? If I look at the next one, once again, simplify and then solve. So I'm going to simplify by doing my distributive property. So here I distribute. I can also distribute the 3 over on this side. So let's see, that gives me in blue. Of course I got to write in blue. Only a crazy person would write the next step in green, right? So I distribute. And now combine like terms. I am allowed to combine like terms on the one side. If you look, I have a 3x and a minus x all on the same side. If they're on the same side, I can continue to simplify before I go into solving mode. So let's continue to simplify. If I combine those, the 3x and the minus x gives me a 2x. And now I can't have variables on two different sides. I got to get rid of one of those. They're both the same in terms of 2x, so let's just get rid of one. I'm going to get rid of this one over here. So to get rid of a 2x, I'm going to subtract 2x. And whatever I do to one side, I have to do to the other side. So what happens is over here, I'm just left with a 6. And over here, I'm just left with a 6. And you're probably going, well, now I don't know what to do. Well, look at the statement that's given. If you have a true statement, it means that I could plug any value in for x and it will work, which means my answer is all real numbers. And the symbol for all real numbers is this little guy. It's like an R with a bar on it. It just means, hey, anything will work for x if I plug it in, all right? If you happen to get a false statement, like here I got 6 equals 6, which is true, But if you get like 6 equals 5, then guess what? Instead of all real numbers, it's no solution. Okay? So watch out for those special cases as well. If I look at this one, once again, distributive property. Over here, I can distribute as well. Let's see, that's a 2x plus 8 minus 4x equals 3x minus 3. And once again, some of these variables are on the same side. The 2x and the minus 4, they're on the same side. I can combine them. Gives me a negative 2x. Now I have to eliminate the variables from one side. Negative 2 is smaller, so I'm going to get rid of the negative 2x. To get rid of a negative 2x, I'm going to add 2x. And whatever I do to one side, I have to do to the other side. And now from here, I just have to solve in the traditional sense. I'm working backwards through order of operations, so I'm going to add that 3 to each side. Well, I'm running out of space. And now divide each side by the 5. And for our purposes in Algebra 2, you can just leave this as an improper fraction. So it says 11 divided by 5 or 11 over 5. Remember, a division symbol is the same as a fraction bar. Done and done. So again, solving equations is just a matter of undoing the process of order of operations. I work backwards. I undo the operations as I go. All right? With the exception of those times when I can simplify first. I simplify until I can't simplify any further. And then I hit the brakes, and now I go into solving mode. Working backwards through order of operations and undoing operations as I go. All right? The last thing we're going to look at here is equations with fractions. All right? And this is a sweet, sweet trick that you're all going to thank me for later. But we can eliminate fractions by multiplying each side by the common denominator. Remember once again that a fraction bar is just a division symbol. So anytime I have a bunch of fractions, I can get rid of all the fractions by multiplying, because it's just a bunch of division. So I get rid of all the division at once by multiplying by the right thing. And the thing that I have to multiply by is the common denominator. For example, if I look at this guy, see, I've got a 1/2 and I've got a 3/4. I've got two fractions here, which makes this thing look ugly, all right? But all I have to do is say, what's the common denominator between 2 and 4? And the answer is 4. But now instead of getting common denominators, I'm just going to multiply each side by 4, and let's see what happens. So I multiply each side by 4, and now this is a case of my distributive property. Watch this, 4 times 1/2, that's like 4 divided by 2. That's a 2x. 4 times a negative 3/4, that's like 4 times 3 divided by 4. That's a minus 3. And then over here, that's a negative 12. And look at how easy this thing is all of a sudden. See, I had a bunch of division, essentially, and I undid all the division at once by multiplying by the right thing. Okay? And I'm going to add the 3 to each side, solving in the traditional sense at this point. And then divide by the 2. And once again, you can leave this as an improper fraction for our purposes. That'll be fine here. If I look at this guy, same thing. Between a 3, a 4, and a 12, what is the common denominator? If I was going to get common denominators, which I'm not, the common denominator would be a 12. So I'm going to multiply each side by a 12. And watch what happens. See, essentially, I'm dividing by 3, 4, and 12. And multiplying by 12 will get rid of all of those division problems. So here we go. Distributive property, our good buddy. This is like 12 divided by 3 is a 4, so that's a 4x. 12 divided by 4 is a 3. Over here, 12 divided by 12 is a 1. So then I'm just left with the 17. Okay? And now the guy is much easier to solve than what I started with. I subtract the 3 from each side. And I divide by the 4. And once again, I can leave it as an improper fraction, but make sure it's reduced, not 14 over 4. Rewrite it as 7 over 2. Okay? If I look at this guy, same thing. Between a 5, a 4, and a 10, what is the common denominator? The common denominator between all of these would be a 20. See, I'm dividing by 4, 5, and 10. 20 will undo all of those division problems. Okay? So I'm going to multiply each side by 20. Let's use my distributive property here. Again, that fraction bar means divided by 5. 20 divided by 5 is a 4, times 3 is a 12. 20 divided by 4 is a 5, times 3 is a 15. And over here, 20 divided by 10 is a 2, times 17 is a 34. That's what a fraction bar really is. It's a division sign. If you think about it that way, operations with fractions become easier. And now I can solve by adding the 15 to each side. And then dividing by the 12. And look at all these really great answers that I went with here. And it's not surprising. Oh, if I could scroll down. When we're dealing with fractions, sometimes things get a little messy. Okay? And then if I look at this last one here, once again, between a 3, a 4, and the 8, what is the common denominator? Well, the common denominator this time is going to be a 24. And so now it's my distributive property. I'm going to distribute this to each fraction. So the first fraction, I just have divided by 3, which gives me an 8x. The second fraction is a little tricky. 24 divided by 4 is a 6, but then it's still times that entire numerator, which is an x plus 2. Don't forget that there's still invisible parentheses here, okay? And I still have to use those parentheses to finish solving this thing. Over here, 24 divided by 8 is a 3, times 5 is a 15. And now I can distribute. That's a 6x plus 12. I can combine like terms. I'm still simplifying at this point. And now I can finish solving. Subtract the 12 from each side. Whoops. Wrong color. It's got to be blue. It's got to be blue for this step. And then divide by the 14. And once again, a really pretty answer for us. But there it is. You can always eliminate fractions by multiplying through by the common denominator. Okay?